So we're going to talk about kinetics. And what we came to before was the Butler-Volmer equation, right? Now, how did we derive the Butler-Volmer equation?
Talk about activation energies.
Talk about activation energies. So what would the activation energy for what process? O plus an electron going to R, a single electron reduction, right?
Yes.
And we had some products, and we had some reactants, right? And so we drew, what did we put on the x-axis? Reaction coordinate, right?
Yes.
Which is kind of the reaction path over this complicated free energy surface. And we're following this free energy surface, and we're looking at the activation barrier. And then we put free energy here. We say, okay, I can have O plus an electron here, has some energy, right? And I can put R here, has some free energy. I've combined the O, where's the electron here? In the electrode, right? So this is electron in the electrode, O in solution, going to R. So the electron has hopped from the electrode to O to make R. And we said, okay, well, this is going to have some free energy surface, and this is going to have some free energy surface as the reaction coordinate proceeds. And these are typically thought to be vibrational modes of the molecule, right? So the O and R, the bonds can vibrate, and that changes the total free energy of O and R. We'll go more through that when we talk about Marcus theory. And then how did I change the direction of this reaction? What's the direction of this reaction as written? Is it going forward or backwards?
It's equilibrium.
It's in equilibrium, so it's going both directions at the same rate, right? So how did I change the direction of reaction? What did I do? So yeah, change the electron potential E, and that changes the free energy of the electron, right? Changes the chemical potential, electrochemical potential of the electron, so I could, if I move the electron potential up, the curve might look like that, and then the forward rate is going to dominate, right? And if I put the electron potential more oxidizing, more down, then the backward rate is going to dominate, right? And then we derived the Butler-Volmer equation, total current. We went through the activation energy analysis, the Arrhenius equation. Remember, we used the Arrhenius equation to write the rate constants for these processes in terms of this applied potential. And then we had this alpha term, which talked about how the potential dropped, how the changes in potential at the electrode affected the crossing of these free energy curves, right? And so we have the Butler-Volmer expression, and we said, well, we can write a cathodic process minus an anodic process. That's going to be our total current, right? The cathodic current minus the anodic current, forward minus backward current. And we said it is equal to Faraday's constant F, A, the standard rate constant, concentration of O at the electrode surface. So this is just from our standard rate equation, right? The rate constant times the number of species that are available to react. That's a standard rate expression. There's our rate constant. But our standard rate constant is modulated by this exponent term that accounts for the fact that the free energy of activation is potential dependent. Right? So there was our forward term. Right? So the concentration of O times this sort of standard rate constant times this term that modulates the rate constant, because these curves move up and down and the free energy of activation changes with applied potential. And then that was our cathodic part. So this was this part, right? It's this part. And then we have to have the anodic part, which is this part, okay? And so let's write the anodic part. So we have to subtract CR 0T EXP 1 minus alpha 1 minus alpha little f E minus E naught, just like that. Okay? So there it is. That's the Butler-Volmer equation. So this is the reverse current or the anodic current. This is the forward current or the cathodic current. We wanted to find something called the equilibrium exchange current. So we can think about this process, right? This equilibrium process you have this electrode surface at equilibrium, and there's some electrons going this way, and there's some electrons going that way. The net current at equilibrium is equal to what? 0, right? But you can still think about it that there's kind of, because of thermal energy, right? Thermal energy is kind of driving a little bit the reaction this way, but the rate of the back reaction is canceling it out completely. So there's no change, but there's still stuff happening, right? Right? Just like there's gas molecules diffusing this way and diffusing this way at equilibrium, though the composition of the gas is not changing on average, right? Okay, so we got that concept. So what is an expression? Can anybody tell me just by looking at this equation what the equilibrium exchange current density is? So these terms have to be equal to each other. Okay, good. What potential will I be at? E equals what at equilibrium? E equilibrium, right? We can define that. So there's going to be an equilibrium potential, right? So at equilibrium, I can make E equals E equilibrium, right? And then these two terms have to be equal to each other. So I can actually define the exchange current density as equal to either of these. C0, or CO of 0T, exp negative alpha, F, E minus E equilibrium minus E naught. So I can find that. This is the exchange current density. I could write it in terms of this too, right? Because they're the same. They're equal. So this is the exchange current density. But this is not in a particularly useful form, right? Because it has EEQ in it. And EEQ is going to depend on what? The Nernst equation. Exactly. Good. So EEQ is going to depend on what? The concentrations of the species, the activities of the species, right? Good. Okay, so we want to clean this up a little bit so we get out that part of it. So I'm going to erase the Butler-Volmer equation. It's big. And so what we can do is we can write EF EEQ minus E naught equals CO star over CR star. What equation is this? Nernst equation, right? This is the exponential form of the Nernst equation. And F, what's F again? Just remember?
NF over RT.
It's an F over RT. It's a normalized Faraday constant, right? Just kind of getting rid of some variables. And N equals 1, right? Yeah, N equals 1 for this one electron process. So if I plug this in and I take the log of both sides, you see readily you get the Nernst equation that you're used to. So this is exponential form of the Nernst equation. And so what I want to do is I want to get rid of this term, or I want to rewrite this term another way. So I want to get rid of this EEQ, right? I don't want the EEQ in there. So what I can do is I can raise this e to the negative alpha EEQ minus E naught equals CO star over CR star to the negative alpha, right? So now I actually have a term here that's starting to look like that term, right? So then I can multiply each side by CO star e to the negative alpha EEQ minus E naught equals CR star to the alpha, right? So I just took that out. So I took CR star, 1 over CR star to the negative alpha is just CR star to the alpha, and times CO star to the negative alpha minus 1. And then I can take my equation for I naught, right? I actually now have an expression here that I can plug in here. So I can say equals F A K naught CR star to the alpha CO star to the 1 minus alpha. Because what is this equal to at equilibrium? At equilibrium, is there any current flowing? Is there any mass transport through the solution?
No.
So what should the surface concentration be equal to?
CO.
The bulk concentration, CO star. I lost some things here, right? So when I wrote the Butler-Volmer equation, I lost my FA K naught, sorry, because that was the prefactor. So what I'm telling you is the exchange current density depends on the standard rate constant. Remember, the standard rate constant is the rate constant under standard conditions, which means you're at E naught and you have equal concentrations of both O and R. That was our definition for the standard rate constant. So this is something that people tabulate. And then the standard rate constant doesn't tell you how fast the reaction is going back and forth at equilibrium. It tells you the rate constant, but not how fast it's going back and forth at equilibrium. And you need to actually know the bulk concentrations to actually get sort of how fast the current's sloshing back and forth, this exchange current. Okay? So it's just the most important thing is you have a microscopic sort of understanding of what's going on. Right? And we just define all these parameters to make it easier to tabulate data and to write the expressions out in a more general way. Okay, so now let's go back to the Butler-Volmer expression, and now what I'm going to do is I'm going to plug in I over I naught. So I'm going to divide everything by I naught. This is a very useful way to think about the Butler-Volmer expression, because now it's sort of like a normalized current. It's normalized to the sort of how fast the reaction is intrinsically. I naught is an intrinsic measure of how fast the kinetics of a reaction are, right? And it gives you some insight into thinking about what type of currents you'll expect. So we get C0, 0t over C O star, sorry, CO of 0t over CO star, e to negative alpha f e minus e naught, e to the alpha f e q minus e naught. Okay, so what I did is I took this expression for the equilibrium exchange current density, right, and I divided it, right, by I naught. Okay, so that's the first term divided by I naught, minus the second term, to the 1 minus alpha f e minus e naught. I gotta go down here, times e to the negative 1 minus alpha f e eq minus e naught. Okay, and there's the second term divided by the other way of writing the expression for I naught. So I didn't divide by, I mean, they're all equivalent mathematically, but I didn't divide by this form. I divided by this form on this side, and I divided by the other form on the other side because they're equivalent, right? The I naught expression for the forward reaction and the reverse reaction, they're equal to each other in equilibrium, right? Okay, so then I can just simplify. The nice thing is what you're going to see here is to this is going to be nice. This term and this term cancel each other. So I have a minus here, I have a minus, and then a minus. So the two minuses is a plus, so these E naughts cancel each other. And these E naughts cancel each other too. So what we're going to see is the expression can be simplified to get it in terms of the equilibrium potential and the actual electrode potential. So it doesn't, what the actual E naught is, remember, E naught's just a reference potential. It's under some given set of conditions. We don't really care. I mean, we like to tabulate E naughts, but any given system, the relevant potential is really the equilibrium potential, where the net current's 0. So if you just stick an electrode in a solution, it will equilibrate and come to the equilibrium potential of the solution, not E naught, right? E naught's some arbitrary potential defined by the reference concentrations we chose to be standard state. Okay, so we can simplify this, and you get I equals I naught, or I over I naught, equals CO of 0t over CO star E negative alpha little f E minus E EQ minus CR 0t over CR star E E, the 1 minus alpha, little f, E minus E, EQ, okay? And this expression is also the Butler-Volmer equation, but you could call it the current overpotential equation, where eta equals E minus E, EQ. So where eta is the overpotential. We learned that variable parameter earlier, right? So, but now we have a formal definition for how the current responds to eta. So what happens when eta is 0? What happens to this expression when eta is 0? Okay, well let's think about it. So what does this term do at eta is 0?
1.
Okay, it's 1, right? This is 1. What about this term? What does this term do at eta is 0? CO star is just it's a constant. CO of 0t is going to be equal to CO star if the current's 0, because there's no transport, right? There's no gradient in concentration. So you have 1 times 1 minus
1 times
1 times 1 equals 0. So the net current, of course, has to be 0 at eta equals 0, at overpotential equals 0. But what this is telling you is you have I naught times 1 going forward and I naught times 1 going backwards. Right? So it's the exact same equation we wrote before. It's just now in kind of a way you can actually handle it. It's getting better and better for handling experimentally. Because you can measure these, you control these, you measure that, you could look this up in the table, or perhaps this is what you want to find for a given catalytic reaction. You might want to extract this value and figure out how good of a catalyst you've made. So these are the types of things people do. So for that, we'll take a little break, and we'll resume talking about this equation in